Coming up on Home Diagnosis.
Pay attention to your heating system.
Today is HVAC setup and commissioning day.
And it was pretty eye-opening for us both.
Testing is likely the most important thing that technicians do or don't do.
First thing to understand is that all this stuff needs to be designed.
It's an applied science.
Home Diagnosis is made possible by support from the ALFRED P SLOAN Foundation, by fantech, Breathe Easy, by Newtone, come home to fresh air, by AprilAire, everyone deserves healthy air, by Air Cycler, RetroTech, and Santa Fe dehumidifiers, by generous support from these underwriters, and by viewers like you.
The house has come a long way since our last episode.
And we've been tuning it to this specific climate.
But almost every place in this country has both winter and summer, and wet and dry seasons. Unless you're in the tip of Alaska or Florida, you'll need a way to keep warm, a way to keep cool, and to turn the humidity up or down.
Grace and I cut our teeth on the science of homes in Chicago, where we needed heat a lot more than air conditioning. We kept warm through 15 winters before coming back to the South, and we were surprised to learn that you need heating more often than air conditioning here in Atlanta, too.
Over the next 2 episodes, we'll dig into the details on heating, cooling, and drying your home. We'll start this episode on heating, where we left off last time with fire.
To explore heating, here's a really quick lesson in thermodynamics. Stick with us. Heat is the thing. Cold is not a thing. It's just the absence of heat.
A little like light with darkness.
Heat can move around in 3 ways. The fire touches the bricks, so the bricks get hot too. That's called conduction. It's also warming the air, which is a fluid that then expands and rises. That's called convection.
And the fire is beaming right through empty space at this side of my body. That's radiation. Heat would happily move in all 3 ways, like it's doing around the fire, but we like to control it in our homes. So let's look deeper into the science of making your home cozy. They say home is where the heart is.
And we certainly put our heart into building our first house. So how hard could it be to build another one?
I'm Grace.
And I'm Corbett.
In our tiny lab, we helped homeowners gain control of their homes through scientific testing. Now, as we build our forever home, we're testing ourselves.
Even though we know a few things about the invisible dynamics of homes, we're teaming up with scientists and building experts to design and build a perfectly tuned home for our family.
The physics, chemistry, and microbiology of a home might seem mysterious, but it doesn't need to be.
While this is a personal story full of twists and turns,
it's also the story of the science of homes.
Join us to unlock the mysterious science of your home, too.
Every build has its challenges and definitely its own timeline. Corbett has been building this house mostly with just his parents, and we suffered from a lot of rain. But this house is starting to look like a house. The first home we owned was a 2-bedroom basement apartment in Chicago. It was small, but we loved it, and we spent a lot of time bundled up on our couch with our cats, listening to our furnace fire up.
That was before we had kids, and the furnace was by far the loudest member of our household. Chicago homes either have furnaces for heating air or boilers for heating water for radiators.
Again and again, we heard people say that forced air furnaces make a home drier, but radiant heating doesn't. Maybe you've heard this too. It seems like common knowledge in northern cities. Problem is, it isn't true.
Whether modern heating systems heat air with fire or heat water-filled radiators with fire, neither one affects the moisture one way or the other in your home as a system.
What might make it drier is if the ducts have holes in them in the attic or the crawl space. Remember, the planes at the top and bottom of any home are where the most air leakage happens because of the pressure of stack effect.
And the pressure of all that hot air being pushed through those leaky ducts. That's why we always focus first on air leakage. If your home is dry in the wintertime, it's almost always accidental air leakage making it that way. If it's feasible to seal up the leaks, do it. And for ductwork, there's always a way to do it.
But if it's not feasible to air seal, there's no shame in installing a humidifier for the cold months to maintain a relative 40 to 50% humidity. The goal is control, because you deserve to be comfortable, and there are lots of tools you can use to get there with your home.
This wall, with no windows and with no reason for anybody to be back here, is where we're gonna put our HVAC equipment. Today is HVAC setup and commissioning day. And so I have two experts. We have Caleb, who drove all the way from Myrtle Beach starting at 3 o'clock in the morning. We also have a brilliant local contractor, Brent Ridley. They are both experts in their field, and they're very well versed in how to tune the actual science, as if this were a lab, even though we're really in my backyard. This is the crawl space I've always dreamed of. All we're looking at right now is we've got some equipment that doesn't yet have ducts on it. We're designing all of the ducts, so we place the boots first. That's where we want all of the air delivered and taken from the space. Then we place the equipment, and all we're gonna do next is connect the two with branches and trunk lines. You need a way to get air to the equipment, which is called a return, and you need ways to get the conditioned air from the equipment into the rooms, which are called supplies. First thing to understand is that all this stuff needs to be designed in a computer normally, not necessarily just on a scratch of paper. Essentially, what you need to do is figure out exactly how many BTUs and CFM you need to deliver to each room in the house, which we have done. Then I had someone do the duct design for me and make a map of exactly how big each duct needed to be, exactly how long it should be, how many elbows it's going to be expected to take. Because of course, every little turn and downsizing I add to these ducts, if I'm trying to squeeze it through little spaces, it limits the airflow. And airflow is the whole thing in this case of a breathing apparatus for your house. Here's a simple experiment that you can run on your own home to find out if your heating system is tuned to what you actually need. Heating systems are selected and installed based on what's called the design day, which is the 99% coldest day of the year where you live.
And when they say today is a record-breaking cold temp, pay attention to your heating system. It should just be on all day long.
If it's not running non-stop and it's turning on and then turning off, it means that it's probably too big, which is an interesting thing to know about your house. You always want to tune the enclosure and the engines together.
And this is a super easy home diagnostic that you can do on your own without any instruments required.
I do think that DIY ductwork is possible when you have the right tools, but I do not recommend DIY equipment installation because frankly, there are just too many tips and tricks and techniques and tools that you just won't know about if you're not a professional who does this all the time. So please do make sure that you consult with an actual professional who has lots of experience in the field before you get yourself into a situation where you might potentially damage the piece of equipment that you're trying to install. What we got here, Caleb?
We have a really tight system, under 50 microns and less than 10 minutes.
Is that your personal record?
It's my personal record, yeah.
Let's boil down to basics really quick. A heat pump is an air conditioner that works both ways. It can take heat out of the house and move heat into the house. It moves heat around. It does not burn something to make heat out of fire. And even as elegant and nuanced as it is, it's really a simple machine. It is 2 fans, one inside the house and one outside the house. And between those 2 fans circulates a loop of refrigerant. You know, I bought this at the store. It said, here's what it can do. We put it into the house. When do you get 100%? Like, yep, it's doing exactly what it was designed to do.
What is our total capacity today?
Total capacity is 8,900.
So we're right on the money of what we should be based on where we're at. So I think we're good to go.
Yep.
Here's something that you always want to see from your contractors that you work with. They're opening the manual and reading it. This is one of the things that we just don't give professionals in the building industry very much of, which is time to think and breathe and just kind of sit with some of the information that they're trying to deal with. These guys are clearly doing all kinds of sophisticated things that, if they did something wrong, would potentially have disastrous effects on the comfort and durability and health of the house that we're trying to build here.
Think outside the box, because just the box there's no box product that's going to solve everything.
Your furnace or your air conditioners, it's tied to an electrical system. It's tied to an air distribution system. It's tied to an air filtration system. It's tied to a condensate disposal system. It's tied to a refrigerant system. And they all interact together. And the home is a system in its own.
Heat flow is a constant in the universe. It's always happening. Warmth is going from things that are hot into things that are cold. It's happening around us, it's happening within our homes. In order to understand how to make the heat and keep it there, you need to understand a little bit more about the metrics. And so we use something like this. You can buy a thermometer hygrometer, or if you just go to the store and ask for something that tells you what the temperature and relative humidity is in a space, they're very available for like 20 bucks. This one is a professional model and it's called a data logger. What this enables someone like me to do is to set this up and get trackable minute to minute or even by the second measurements of temperature and relative humidity, and a third measurement, which is dew point. Dew point's important to understand because the main difference between indoor spaces and outdoor spaces is the huge amount of surface area inside, and dew point is all about the interaction of the air's temperature and humidity with surfaces. So if I want to be able to predict and prevent surfaces becoming wet, because that's my nightmare, then what I would do is understand more about the metrics, which is of course what we're doing on this show. And so we used this to set up in this workshop to start with, because this workshop is the closest thing to an outdoor space that you're going to get. It's not conditioned. In fact, birds can fly in and out of here, and they do all the time. I don't have screens up. It's not insulated, it's not air sealed, and there's no equipment heating or cooling it or drying it. It's shaded, which is nice, and that's something that is not going to account into a graph of the weather that looks like this. So you can see that the temperature goes up in the daytime when the sun comes out, and it goes down again at night. Meanwhile, the relative humidity goes down in the daytime and goes up again at night. There tends to be a pretty consistent level of moisture in the air, and so when the temperature goes up, relative humidity goes down. But there's a third measurement in this graph, and that is dew point. The dew point, you can see, is tracking a little bit with both because it's about the relationship of those two things with the surface. So in this space, the graph looks almost identical to the weather graph that we see. My graph is a little bit more detailed because my equipment is a little bit better. I'm able to get minute-to-minute readings instead of just hourly. So this space is a good way to understand the most minimal utilitarian shelter we could have, where we're just trying to keep the rain out, we're trying to keep big animals out of here and people, and we're trying to make sure that wind doesn't blow things around in here. Not very sophisticated. Let's look at a couple other spaces where we're trying to use some of the techniques that we show in home diagnosis to try and harness the power of heat flow. Now this is the first step towards making a space that's a little easier to condition.
So this is actually one of the original structures on our property. It's the old spring house. And I mean, you couldn't even see it when we got here. It was so overgrown, there was a tree growing out on top of it. So we call it Troll House.
So this troll house has something that the workshop did not. It's called thermal mass. It means it's made out of heavy stuff. That makes it harder to heat up in the morning, and it retains its heat at the end of the day when the sun goes down. If your house is made out of something like solid brick or concrete or stone, then it would have thermal mass, which is a nice thing, but you can see that it's not insulated or air sealed, so it's not really like a house. But it is considerably more controlled than the workshop was, where the workshop can change temperature on a dime and the graph looks very ragged. This space looks a lot more smooth, and you can see even that when the sun comes up in the morning, starts warming it up, but then it moves into shade and it dips right back down, which is something that you would not have seen with the workshop.
So thermal mass is a first step towards controlling your heating and cooling.
Now we're getting closer to a place where you could actually think about living.
Welcome to our build. Now, if you look at the graph for the build, you will see the benefits of air sealing and insulation.
And that's it. Since it's under construction, there's no heating and cooling equipment at work in here. And all you're seeing is the little bit of insulation that's outside the walls. There's not even any in the roof yet. This is how you start to really tamp down on the way that the weather tries to yank your living space around.
But this really isn't real life. So let's go see what real life looks like.
This is the space where we keep our testing equipment and some of our belongings that didn't fit into the tiny lab. Now this space also has thermal mass.
The thermal mass is an 8-inch concrete slab that's in contact with the ground.
It also, obviously, since you know us, is airtight and insulated, but it has a piece of equipment at work in here.
The magic dehumidifier, which we're gonna get into moisture more in the next episode.
But for right now, you can see this one piece of equipment at work in the graph very clearly. I can use this information to find out if it's doing what it's supposed to be doing, how hard it's working, but we're still not really in real life because you are never gonna have just one piece of equipment at work in your house at any one time.
Now we come to the temperature behavior of a real-life lived-in house,
Where we have not just one, but two pieces of equipment that are hopefully working in tandem to tune the space.
we have the HVAC system and a dehumidifier. And if you look at the graph of this house, it's much smoother, right? Except for you got real life. Like, for example, the big jump where my daughter left the door open.
Or you forgot to set the dehumidifier back to the level that the baby changed it from the other day, or somebody leaves a window open, somebody leaves a fan on. These things happen, it's okay. But we hope to, in the final episode of this season, show you what looks like almost a perfectly flat line in our big house that we're building.
Using a systems approach is how you can control your own home's temperature behavior.
Most consumers have never experienced comfort in their lifetime in their home, and they don't even realize it. It's like having a nail in your hand for 30 years and you don't realize the nail's there. You learn to live with a nail. And people do it all the time. They have headaches in their homes. They're sick. They have allergies. They're taking medicine. They live with all these symptoms, and they just figure that's the way it is. We have the solutions. We've had them for 20 years. We have the technologies, but we don't have consumers that are asking for them, and we don't have contractors that are confident selling them.
Since the 1970s, there's been research done on thermostats, specifically how you can use your thermostat to do cool stuff.
The cool stuff in the 1970s was learning to stop wasting energy. It was an important goal at the time, and it still is, but as we like to point out on this show, home performance is not all about saving energy. How your home feels to you is important too.
Using a thermostat to save energy and using it to keep a home feeling good are not the same thing. Take our tiny lab, for example. Let's say I program the thermostat here to relax while we're away for a few hours or overnight to save energy. And the house temperature starts slipping toward the outdoor temperature.
Once the thermostat is turned back to the more comfortable temperature, I notice the strangest thing. I'll still be cold for what feels like a long time, even though the thermometer right there says that the air is warm.
Whether we heat forced air or radiant surfaces, both the air and surfaces need to equalize and come to the same stable temperature. When we let the indoor temperature slip for a while, the air might warm up again quickly because it's so lightweight, but the solid stuff takes a lot longer to warm up.
In here, our bodies are always right next to an exterior wall, floor, or ceiling, and those solid surfaces are sucking the heat right out of us to get back up to the temperature. The same thing is happening in your home too, but it's probably a little bigger than our 200 square foot tiny lab, so it'd be hard to put your finger on exactly what's going on.
This is why the same 72 degrees can feel so different from winter to summer. Anyway, if your home is equipped with good air sealing and insulation, it takes a lot longer for anything to warm or cool. So setting your thermostat back doesn't save much energy anyway. We prefer the set it and forget it approach for thermostats. Pick your favorite number and walk away.
Oh, pick my favorite number.
Pick her favorite number and walk away. That's what I like.
It's always nice when you start up your newly designed duct system because you always want to hear what it sounds like, and it's like, is it going to perform exactly like I wanted it to?
Right. So we turned on the system and it runs, and you can hear it run and you can feel it run. But of course, how it runs and how it turns out over the next couple minutes is very important. So you don't want to just turn it on and then leave. Brent, you found out first that
Our lines were starting to freeze up. You know, we started to have frost build up on our refrigerant lines, so that was saying, hey, something's going on.
yeah, specifically, that's kind of a key indicator that the air is not moving like it should. And so we first tested the pressure, 0.03, which for HVAC speak is 0. That means no air is moving through this. There's no pressure. And this system has dampers all over it because you know I like to control and tune things. We got over here to the two main trunk lines, And both of those were totally shut. At some point, somebody, probably me, had just brushed past them and closed them. Testing, even of the sort that we've done so far with static pressure testing and things like that, does that happen on a course?
Not really. It doesn't happen very often. You know, it has to be specific applications and things like that. It should be done every install, every startup, but unfortunately it doesn't happen that often.
Yeah.
I had an epiphany on my own years ago. When I got into the classroom, I was a teacher for 12 years at a vocational school. And I had the luxury of time for the first time in my career to actually stop and look at things and understand how they worked. I found out no matter how hard I tried, I couldn't get the same answer twice. And it just happened over and over and over again. And finally, I just said, there's some things that we just can't do in the field. They can only be done in the lab. And he goes, Bergman, we are in the lab. It was not about the science that didn't work in the field. It was the tools that didn't work in the field. And I was trying to do all this complex work with a very rudimentary set of tools to do so. We're actually at a wonderful time in our industry because technology that was only available in the lab years ago now is easily available to any technician in the field. But we also have an industry that hasn't quite learned how to use them and apply them. And so we're playing catch up. Testing is likely the most important thing that technicians do or don't do. And it's been a challenge in our industry since the industry started.
Every home has engines. You're gonna have to deal with it. So you should make space for them and plan where exactly all of the ducts and pipes and machines are gonna go.
This is a central chase. Now you can see all the way up to the roof.
I'm proud to say that in every version of the plan for this house, which has changed a bunch of times, we have had this central mechanical chase, also known as a shaft, that's going to just contain all of this stuff and make it really easy for it to be all in one place, consolidated. It all makes sense in here. First of all, we've got over here a central vacuum system, which I'm going to talk about more later in the season. We have 2 drain lines that are these PVC pipes. We have an insulated heating and cooling duct that's also sealed inside. We have 2 sealed ventilation ducts that I'm going to talk about more later in the season as well. One taking stale air from the second floor, one sending fresh air to. And we have this, which is the only water line that's going up to the second floor. I think you might be missing something, Corbett. You might be thinking to yourself, where's the hot water line? Well, we're going to get by without doing a hot water line throughout the entire house. You're going to call for hot water and you're going to instantaneously get it. It's a little bit of a weird way to do it in the United States of America, but in other places in the world, they do this all the time. In a lot of places we've lived in, you turn on the water in the shower and then you wait 5 minutes to get in. We thought that we'd go ahead and be the guinea pigs and try it out, see how it works. So let me take you down to the crawl space and show you the rest of the layout of the mechanical system. This is one of our 5 point of use water heaters. Essentially, we've got 5 zones. The kitchen is where we are right now. We have a much bigger one of these underneath the master suite and laundry. And then we've got the other bathroom zones in the house. And the idea is that we've got water coming in, that one cold water pipe everywhere throughout the house, comes into the machine, gets heated to a very specific temperature that you can set, which I think is very important, to be able to dial exactly what temperature you want. And then it leaves to be distributed to the hot water fixtures. Now, this is a microprocessor controlled piece of equipment, which means that if I had a sink on and then I was to suddenly turn on another sink, this will up its output. And in fact, this thing can run about 14,000 watts, which is a lot. Some people might say, that's not an energy efficient way to heat water. You could do recirculation loops where you heat water and then you just have it go around and around and around the house all the time. All of these have their trade-offs. So don't let anybody ever tell you that there's only one way to do something, because that is absolutely false. If you want your bathtub to actually hang on to temperature, number 1, don't put bathtubs on exterior walls. Next, this is an acrylic tub. It's not going to hang on to the temperature very well. But what you're going to add to the hollow body of this is insulation. We had a bunch left over from insulating the walls, and we're done. One other thing about this is that it has a low flow activation. And this is something that you should really watch out for if you use any kind of a tankless technology, including point of use. For example, the sink in our powder room, which is a half a gallon a minute, which is one of the water efficient fixtures that we have in the house. If I was to turn that all the way on hot, some of the bigger units that you might see that serve an entire house won't even know that you want hot water. Think about what the system needs before you start tailoring the fit with pieces of equipment that will help your home performance. If you're going to warm air in a home, there are 3 main ways to do it. You can use gas, natural gas or propane. You can do it with electric resistance, or you can use a heat pump. It used to be that a heat pump would really only work efficiently down to about 30 degrees air temperature outside. Of course, when you really are going to need your heating system is when it's really, really cold. So here in Atlanta, we get down to 22 degrees is our design day temperature. That means that I can expect that it will get to 22 degrees and even a little bit colder than that on an annual basis. And nowadays, the heat pump technology has evolved to the point where this heat pump right here, which they are also installing in places like Montana or Alaska, can run down to negative 25 degrees. You're losing efficiency at that point, obviously. It's not going to work quite the same way. Kind of incredible, though, to think that you can squeeze heat out of air that is negative anything degrees.
When Corbett and I started in home performance testing, we worked with low-income weatherization programs. We went into a lot of homes where families couldn't afford to keep up with the maintenance on the house they inherited, and it was pretty eye-opening for us both. A lot of gas and oil-burning heaters we tested were literally one bad day away from hurting the kids that live there. All HVAC equipment needs regular checkups, but especially machines that burn fuel. For the people who can't afford the help, luckily there are publicly funded programs. But we've seen a lot of dangerous heating equipment in homes that could afford the maintenance too. Don't forget that even with top quality home heating machines, your home is only as safe as you make it. Once a year, pick up the phone and schedule a checkup, just like we do with our personal health. And remember to ask for testing, just like you see here on Home Diagnosis.
Of course, there is so much more we could talk about on the topic of heating homes, but this is a half-hour show.
So go hunker down at homediagnosis.tv to learn more magic about controlling the invisible physics around you. We'll see you next time.
A bug totally just flew in my face. The bugs are starting to come out. Ooh, the sun is coming out. Yeah. And I want to take this sweater off too. But
We're still in heating episode.
We're still in the heating episode.
And Grace has me in a sports bra, which is keeping my microphone quiet. So just use your imagination on that one.
Home Diagnosis is made possible by support from the ALFRED P Foundation, by fantech, Breathe Easy, by Brown-Newtone, come home to fresh air, by AprilAire, everyone deserves healthy air, by Air Cycler, RetroTech, and Santa Fe dehumidifiers, by generous support from these underwriters, and by viewers like you.